In the previous video, we talked about yaw control. In this video, we will talk about pitch control. Not all wind turbines are equipped with pitch control systems. For small wind turbines, the benefit of pitch control may not justify its cost, so most of the pitch control systems are found inside medium-sized or large wind turbines. So what exactly is pitch control, right? In its simplest form, it's just rotating the blade around its longer axis in order to change the angle of attack of the relative wind. Right. I will explain what exactly is what exactly does it mean, right? By changing the angle of attack of the relative wind. Later on, it will become more and more clear. Right. The mechanics of doing this rotation actually has some similarity with the active yaw system, with the active yaw control system we talked about in the last video. So here inside the rotor hub, so this whole thing is inside the rotor hub. It's inside of this thing, right? It's inside of this thing. So here we have a small electric motor that's going to drive this small gear, and the rotation of this small gear is going to drive the rotation of this large ring gear, which then rotates the blade around its longer axis, right? This is an electric pitch control system, right? Because it's driven by an electric motor, but there's also the so-called hydraulic pitch control system. It's not shown here, but there's another option, right? It's called hydraulic pitch control system. This kind of hydraulic pitch control system uses hydraulic pumps instead of electric motors to turn the blades. Right. And each type of pitch control system has its own advantages and disadvantages. But how exactly does the pitch control system change the aerodynamic torque? Back in video 11, we talked about why the wind turbine blades, especially those large long blades on large wind turbines, usually have a twisted shape. Here this plot actually shows that the blade twist angle, how the blade twist angle changes along the blade length. Here it's the normalized radius. The non-dimensionalized blade radius is basically along the blade length, from the root of the blade towards the tip of the blade. Right? That's the horizontal axis. The vertical axis is the blade twist angle. So at the root, close to the root of the blade, the twist angle is almost 60 degrees. But at the tip of the blade, the twist angle is 0. So the blade is actually twisted. Right? The explanation that we talked about in video 11 was that the reason for having a twist is that we would like to keep the angle of attack of the relative wind at the optimal value, which is actually a fixed value for a given airfoil. So if you are using the same airfoil throughout the length of the blade, then this optimal value of angle of attack is a fixed value, right? So in order to maintain this optimal angle of attack throughout the length of the blade, we have to actually change the twist of the blade, change the twist angle, right? So the vector of the relative wind, UREL, this vector, it's actually the vector summation of the free stream wind speed. That's this vertical vector here, and the negative of the linear speed of the vector of the airfoil. That's the horizontal vector here, omega r, right? Those are the induction vectors, right? But let's sort of forget about the induction vectors for now, right? Let's just assume the vertical vector is u1 without the -8. And then the horizontal vector, that's the linear speed of the airfoil located at radius r, right? Let's forget about the a prime. It's just the omega r. Omega is a constant, right? And r varies, right? At the root of the blade, r is small, and at the tip of the blade, r is large. Right? So the linear speed of the airfoil actually varies with the length of the blade. So close to the root of the blade, r is small, so the linear speed is small. Omega is a constant, right? And at the tip of the blade, r is large, so omega r is large. So this vector is longer close to the tip, right? And so if the free stream wind speed is a constant, right? As we move from the root towards the tip, this vector is gonna get longer and longer, right? If this vector gets longer, then the vector for the relative wind is gonna rotate towards this horizontal direction. So as we move from the root to the tip, this vector increases, this vector length is fixed, right? So if this vector becomes longer and longer, then the relative wind is gonna go this way, and the angle of the relative wind phi is gonna reduce towards the tip of the blade, right? So if this phi actually reduces, if we want to maintain the angle of attack at a fixed value, at a constant value, the only thing that we can do is to actually reduce theta p. That's the section pitch angle. Theta p, right? That's the section pitch angle. So angle of attack is the angle between the relative wind and the chord line of the airfoil, right? And the section pitch angle is the chord line. The chord line is the angle between the chord line and the plane of blade rotation, right? So as we move from the root to the tip, phi reduces, right? And phi equals to theta p plus angle of attack, right? If phi reduces and we would like to maintain the angle of attack at the optimal value, we have to actually reduce theta p. Reducing theta p means rotating the airfoil, right? Rotating the airfoil chord line, right? So by rotating the airfoil chord line, we actually introduce a twist into the blade, right? That was the reason that we gave when we were explaining the twist in the blade, right? So how was the optimal angle of attack was determined, right? So for a given airfoil, the optimal angle of attack is determined based on the ratio between the lift coefficient and the drag coefficient for that particular airfoil. So if you pick an airfoil, then you have a CL over CD curve, right? And what you would like, this CL over CD curve actually varies with the angle of attack. This kind of curve can be computed for different kinds of airfoils. You can think of it as a given thing, as a given information, given data, right? So the optimal angle of attack is picked at CL over CD is the maximum, right? For this particular airfoil, the optimal angle of attack is like 6 degrees or something, right? Sometimes this kind of curve is plotted as CD over CL instead of CL over CD. If that's the case, you would like to find the angle of attack which gives you the minimum of CD over CL, right? Gives you the least amount of drag, basically, right? So that's how we actually found the optimal angle of attack. The fundamental reason for pitching the blade, for turning the blade, is actually similar to the reason for twisting the blade, right? In our analysis in video 11, we were basically assuming that the free stream wind speed u1 is kept constant. It doesn't change, right? But we know that the free stream wind speed u1 actually varies with time, right? It can change with time. So suppose the wind speed is below the rated speed, and the goal of the control system is to maximize power output, right? So at a given radius, if we look at just the airfoil at a given radius, r, so r is fixed, right? We are just looking at a particular cross-section at a given radius, right? If r is fixed, then omega r is fixed. So the linear speed of the airfoil is fixed, right? So if the free stream wind speed u1 increases, so if this vector actually becomes longer, right? Then the vector for the relative wind is going to rotate this way, and the angle of the relative wind phi is going to increase, right? If the u1 actually increases, if u1 increases, then phi is going to increase, right? So in order to actually keep the angle of attack on this airfoil at its optimal value, we need to actually increase the section pitch angle theta p by turning the leading edge of the airfoil towards the incoming wind, right? On the other hand, if the free stream wind speed u1 decreases, if it actually becomes shorter, this vertical vector becomes shorter, right? Then urel is going to rotate the other way. It's going to go this way, and phi is going to decrease, right? So the angle of the relative wind is going to decrease. If that's the case, and we want to maintain the optimal angle of attack, then we have to actually reduce theta p by turning the leading edge of the airfoil away from the incoming wind direction, right? We have to rotate the airfoil the other way, clockwise, in this direction, right? So that's by fixing. So if r is fixed, right, we are looking at a particular radius, right, and if we vary the incoming wind speed, right, if u1 actually increases or decreases with time, then how we are supposed to actually change the pitch angle of this particular section of the blade, right? But how does the control system know when and to which direction to pitch the blades, right? So for a human being, it's kind of easy to actually see how to actually change the pitch of the blades. But how does the machine know, right? How does the machine know? So here is the CP lambda curve that we have looked at in video 13 and also in video 24, right? We looked at this CP lambda curve in several previous videos, actually. So the control system actually has a record of the optimal tip speed ratio lambda OPT, which gives the maximum power coefficient, the CP-OPT, right? This record tip speed ratio is sometimes called the reference tip speed ratio, or reference TSR. On the other hand, the control system can obtain data about the instantaneous tip speed ratio because it knows the rotational speed of the blades, and the anemometer can give it data about the free stream wind speed, so it can compute the instantaneous tip speed ratio at any time, right? The tip speed ratio is just the ratio of the linear speed at the tip of the blade and the free stream wind speed, right? So the control system actually knows the instantaneous tip speed ratio at any time. So if the instantaneous TSR deviates from the reference TSR, if it becomes smaller than TSR or larger than TSR, then the control system will know that it has to sort of do something about the pitch angle of the blades. But in which direction, right? In which direction should the machine actually pitch the blades? It will try. It will pitch the blades in one direction first, and see if the power coefficient increases or decreases. If the power coefficient decreases, then it means that it has pitched the blade in the wrong direction, and then it will pitch the blade in the opposite direction. So if the blades are pitched in the correct direction, the angle of attack will then gradually return to the optimal value. So suppose the TSR is lower than the reference TSR. We are operating at the TSR that's sort of smaller than the reference TSR, right? As the angle of attack returns to the optimal value, the lift forces and the torque on the blades will increase, right? And the blades will rotate faster. And then the TSR will gradually return to the reference TSR. So it's going to move towards the optimal CP also, CP-OPT also. It's going to go this way, right? And if the instantaneous TSR is higher than the reference TSR, Right? As the angle of attack returns to the optimal value, the lift force and the torque on the blades will decrease, and the blades will rotate slower than TSR, and the TSR will again go back to the reference TSR. In practice, there is a problem with this kind of pitching strategy. The CP lambda curve may not be available for the specific wind turbine we are trying to control. Right? This curve may not be available. Right? Even if the CP lambda curve is available at one time point, say when the wind turbine was brand new, the characteristics of the wind turbine can change with time. Therefore, the CP lambda curve can also vary with time. So the CP lambda curve you have may not be accurate for the current time being, right? So if the CP lambda curve is not available, how do we actually pitch the blades, right? There is another approach that is based on the shape of a typical CP lambda curve. Usually the CP lambda curve has only one peak. It has only one peak. And the curve is usually smooth around this single peak. So at the peak, the derivative of the power coefficient with respect to the tip speed ratio is zero. Right? Because it's at the peak, it's at a stationary point. So what's the necessary condition for a stationary point in calculus, right? It's the derivative at that point must be zero, right? So if the derivative is zero, it means what? It means if you change the TSR by a small amount, you are not going to change CP, right? That's what the derivative being zero actually means, right? Which means a small change in TSR produces zero changes in CP. But if we are not at the peak, if we are at some location that's very far away from the peak, right? Then the derivative is not going to be zero, right? It's going to be either positive or negative depending upon which side you are. If you are on this particular side, it's probably going to be a positive slope, but on this side, it's going to be a negative slope. But as long as it's not at the peak, then the derivative is not going to be zero, which means that a small change in TSR is going to produce non-zero change in CP, right? So the control system can be designed in such a way that it can detect the amount of change in CP caused by a small change in TSR. So if a small change in TSR produced zero or negligible changes in CP, the control system knows that it has reached the peak of this unknown CP lambda curve, and then we'll stop pitching the blade, even pitching the blades further. The pitching strategies we have talked about so far are for wind speed below the rated speed, and the goal of control is to actually maximize energy output. So what if the wind speed is actually above the rated speed? We are in this particular region, right? Under this kind of situation, the goal of the control system is to regulate the power output. We actually need to flatten the power curve, right? So the goal is different now, right? In this region, the wind has more power in it, but we need to actually limit the amount of power we extract from the wind. So when the wind speed is above the rated speed, what are the options we have, right? We cannot use electric torque for regulation purposes, even if we have a variable speed wind turbine. The reason is that above the rated speed, the electrical system is already saturated. It's already operating at its maximum capacity. So if we want to reduce, for example, the rotational speed of the blades, we cannot actually increase the back torque. We cannot increase the back torque, which is the electrical torque from the generator. We cannot do that because the generator is already running at its maximum capacity, right? Increasing the back torque or increasing the electrical torque will just burn the generator, right? We cannot. So electrical means is not available to us anymore, even if we have a variable speed wind turbine, right? So the only solution the only solution is to reduce the aerodynamic torque, right? Whether the turbine has a variable speed generator or not, right? The only way for us to regulate the power is through aerodynamic means, right? Through mechanical means. So under such situations, we can pitch the blades in a way such that the angle of attack deviates from the optimal angle of attack. So for this particular airfoil, the optimal angle of attack is at about 6 degrees, right? We can pitch the blades either to reduce the angle of attack to below 6 degrees, or to increase the angle of attack to above 6 degrees. Decreasing the angle of attack is called pitch to feather, and increasing the angle of attack is called pitch to stall. In either case, the lift coefficient to the airfoil will decrease, and the drag coefficient of the airfoil will increase, which will limit the amount of lift forces and also the torque acting on the blades, right? Because the lift coefficient is decreasing with respect to the drag coefficient, so the lift forces are going to decrease, right? From the blade element momentum theory, we know that the torque is pretty much determined by the lift forces, right? So if the lift forces are decreasing, then the torque acting on the blades are going to decrease, right? Are going to be limited. Right? So if we reduce the angle of attack, if we choose this particular path, right, in the limit, we reach an angle of attack of 0, right? So this is the direction of the relative wind, and if the angle of attack is 0, which means that the direction of the relative wind is kind of a parallel to the chord line of the airfoil, right? So this is actually the feathering condition. So the orientation of the airfoil is almost aligned with the direction of the relative wind. Right, this is a picture of airplane propellers. The blades on the left propeller have non-zero angle of attack and are working under normal conditions. But the blades on the right propeller, this one, are under feathering condition. So you can sort of see what feathering condition is going to look like, right, on a propeller. On wind turbine, it's kind of similar, right? It's kind of similar shape and similar kind of angle. We talked about the stall condition. So now let's look at going this way, right? Pitch to feather is more or less like that, and let's look at this particular path, pitch to stall, right? We talked about a stall in video 7, right, when we were discussing properties of the airfoil. So this is low angle of attack, this is high angle of attack, this is even higher angle of attack, right? So when the angle of attack exceeds a certain threshold, the streamlines, or the white lines, can no longer follow the upper surface of the airfoil, and then they detach from the upper surface. See, here the streamlines are still following the upper surface, right? But here the streamlines are not following the upper surface. It has detached from the upper surface. Right? At this point, the airfoil is going to experience a sudden drop in lift force, and this phenomena is called a stall. So by pitching the blades to increase the angle of attack, we can deliberately induce the stall condition on certain portions of the blades. Right? By inducing stall, we can limit the total amount of lift forces and also the torque acting on the blades. And this pitching strategy for regulating aerodynamic torque is called active stall. Right? We are actually deliberately changing the pitch angle, changing the pitch angle using active using the pitch control system. Right? And this is called And the store induced using this kind of scheme is called active store, right? And for wind turbines that do not have a pitch control system, for example, small wind turbines with fixed blades, you cannot turn the blades. It is still possible to induce. It is still possible to use store to regulate the aerodynamic torque above the rated wind speed, right? And if you cannot turn the blade, and the store that the turbine can actually produce is called passive store, because it's not sort of a store that's induced actively using the pitch control system. So it's called passive store, right? So how passive store actually is produced, right? This is the front view. This is the front view of the rotor with three blades. Suppose all the blades are fixed to the rotor hub. They cannot be pitched, right? They are fixed blades. We can take a top-down view from this particular direction, right? And then look at the cross section. Look at cross sections at different radius r. That's a radius, right? So from this top-down view, the plane of rotation, the plane of blade rotation is going to be this horizontal black dash line, right? And then the cross section are going to appear as these kind of the cross section of the blades are going to appear as these kind of airfoils, right? And the linear speed of the airfoil is going to go this way, right? And so everything else is going to move in this direction, right? That's sort of the negative of the minus of this particular omega r vector, the linear speed vector. So it's going to point in this direction, right? So if we draw the velocity triangle for the airfoil at the root of the blade, and also draw the velocity triangle for the airfoil at the tip of the blade, at different free stream wind speeds. This is for small free stream wind speed u1, and this is for large u1, right? So what's going to happen, right? What's going to happen? So suppose we look at the small u1. So u1 is fixed. Right? So at the root of the blade, r root, the radius is going to be smaller. But at the tip, r tip is going to be larger. Right? Omega is the same. The angular speed is the same. Right? So the linear speed at the root is going to be shorter. And then the linear speed at the tip is going to be longer. It's going to be larger. Right? So if we compare, so the relative speed is just this black arrow. Right? It's sort of the vector summation of this green arrow and the red arrow. Right? So the green arrow is the same for both cases. Right? And then the UREL, that's the relative wind speed, is the black arrow. So if we look at the angle of the relative wind, so phi at the root is going to be larger than the phi at the tip. Right? So this is going to be a larger phi. If the phi is larger, which means what? Which means the angle of attack is going to be larger. Right? Suppose the twist angle is about the same. Right? So for small wind turbine, you may not have a twist. The turbine may not, the blades may not be twisted. So let's suppose there's no twist. Right? If there's no twist, then phi, if the phi is larger, then the angle of attack is larger. Right? Now suppose we increase the free stream wind speed u1 gradually. Right? If we increase u1 gradually, the angle of the relative wind is going to increase also. Right? If we compare these two, so red arrow is the same length, but the green arrow becomes longer. Right? So as the green arrow becomes longer, phi increases, which is true for both cases, right? But because at the root phi is larger at the beginning, at the smaller u1, so at the root, the blade is gonna enter the store regime earlier, right? Suppose we are using the same airfoil along the entire blade, so the threshold angle over which the airfoil is going to enter the store regime is the same, right? And because at the root phi is always bigger, so the root is going to enter the store regime earlier, right? And if the free stream wind speed keeps increasing, then the region under the store condition will expand gradually from the root outward towards the tip. So even without an active pitch control system, the fixed pitch wind turbine can be designed in a way such that when the wind speed exceeds the rated speed, larger and larger portions of the blades will automatically enter the stall regime. And this is called passive stall. It's not induced actively by turning the blades. It's just designed in such a way, right, so that when the wind speed is over the rated wind speed, portions, larger and larger portions of the blades is going to enter the stall regime, right? And this is called passive stall. The power curve for the wind turbine using passive stall may have a small hump. It may have a small hump around the rated wind speed. Right? This is the zone in which the wind turbine transitions from one mode of operation to the other mode of operation. So because it takes some time for the passive stall to propagate from the root outward, so for a short period of time, the wind turbine may still operate, may operate out of the limit of the rated condition. Right? If there is a pitch control system, those by inducing active stall actually takes a shorter amount of time. So the power curve, for active stall machines is relatively flat above the rated wind speed. Right? So pitch control can actually bring the power curve closer to the ideal situation.